So moving to chapter 4, we start looking at vectors. And most of us, I'm sure, have dealt with vectors before. And the vectors that we've dealt with have been two-dimensional vectors and three-dimensional vectors. And remember what vectors are in a geometric standpoint, used in physics, engineering. A vector is basically a directed line segment. It has direction and it has magnitude. And we've used this notation to represent a vector. In Math 113, calculus, we often list a vector like such. And we'll list them in component form in this book, but typically instead of using these symbols on the end, then we'll list it like this. And generally when we think of vectors, we are going to think of them as a directed line segment. As we get into 4 dimensions, 5 dimensions, 6 dimensions, etc., we can think about them kind of as points in a plane or as a directed line segment, but then you have multiple dimensions, so the same thought process doesn't quite follow through all the way. But even though we're writing these differently, and even if we go into multiple dimensions, if we have u being 4-dimensional or 5-dimensional, the same operations hold true as do for traditional vectors that we think of geometrically. If we want to take a vector and add it to another vector, we just add corresponding components. If I've got vector 1, 2, and I want to add that to vector 3, -5, then we just add the first components together, add the second components together, next our vector u plus v. If we have a vector that we want to multiply by a scalar, if we have, let's say our vector is 3, -4, then we multiply each component by that number. So 3 times 2, -4 times 2. So 6, -8. There are a list of 10 properties in our book of vector addition and scalar multiplication, which addition and subtraction kind of go hand in hand. So let me get my notebook tools back. Copy this table over. And most of these kind of are just common sense. If we have 2 vectors or 3 vectors in a plane, if I take one vector in a plane, add it to another vector, then my answer is going to still be a vector in that plane. For example, if we think about the xy plane, if I have vector 2, 3, and I add it to vector 0, 1, both of those are in the xy plane. If I add those together, I still get a vector that's in the xy plane. Also, if we change the order, instead of doing this vector plus this vector, if we swap them up and do v first and then u, either direction, we get the same answer. If we add 3 vectors, it doesn't matter the order that we're adding them together, because eventually all the first components are getting added together. All of the second components are eventually getting added together. So whether we add the first two and then the third one, or the second and the third one and then the first one, associative property still holds. When we see this one, that stands for the zero vector. So if I'm adding 2, 3 to the zero vector, that's basically the vector 0, 0. So if I add 0 to anything, I get what I started with. This says that there's an inverse, so if u is 2, 3, then the additive inverse, the opposite of that, would be -2, -3. Basically, -1 times vector u, -1 times each component. Remember when we multiply by a scalar, geometrically what that means is we're going in the same direction, we're just changing the length of that. So, for example, if vector u is 3, 1, we could start that anywhere. For convenience, we'll start it at the origin. If I want 4u, that means geometrically that I'm going u 4 times. So I've got it once, twice, 3 times, 4 times. So if I were to do 4 times each component, 4 times 3, 4 times 1. So I have a net change up to the right 12, up 4. Now, it would have helped if I'd have drawn my first vector straight so that it would have indeed looked like a straight line. But geometrically, that's what we're doing. When we multiply by a scalar, we're keeping the same direction, we're just changing the length of it. But again, the way we do that operation, multiply each component by that number. Now, you might be thinking, well, this sounds really similar to things we said before. Sometimes it helps to represent a vector as the row matrix. So vector u, which was 3, 1, we could just write that as a row matrix, a single row, or we could write it as a column matrix, a single column. So either of those sometimes we could use to represent that particular vector. Just another notation of representing the same type of thing. So let's do 1 or 2 problems, and that should be sufficient for 4.1. If we have vector u, which is 4, 0, -3, 5, and w, which is 0, 2, 5, 4, let's get u minus v, which to do u minus v, we take each component in u and take away the corresponding component in w. It's supposed to be w, not v. So 4 minus 0, 0 minus 2, -3 minus 5, 5 minus 4. If I want to do 3 times 2u minus 4w, of course we need to start on the inside. So let's write out what 2u would be. 2u would be 2 times each of these, so 8, 0, -6, 10, minus 4 times each of those, so 4 times 0, 4 times 2, 4 times 5, 4 times 4, So if we combine the two vectors inside, 8 minus 0, 0 minus 8, negative 6 minus 20, 10 minus 16. And then we do 3 times that, so 24 minus 24 minus, let's see, 3 times 6 is 18, carry 1, 78, minus 18. So we would have that. Now, when we say that something is a linear combination of something else, let's say of U and V. Linear combinations means that we're not taking our things and multiplying them together or raising them to powers. It means we're taking them, adding them together. We could have multiples of either one of them, but we're just adding a multiple of things together, and that's a linear combination. If we had more vectors and we wanted a linear combination of all three of these, then we would just add scalar multiples of all of them together, and that would be a linear combination. So let's look at an example. One problem says, find W such that 2U plus V minus 3W equals 0. And they're going to give us that U is 0, 2, 7, 5. V is negative 3, 1, 4, negative 8. So essentially, we can rewrite W as a linear combination of these vectors. If we solve this for W, we can add 3W to both sides. We could divide both sides by 3 or multiply by the scalar 1/3. So this gives us how W is related to U and V as a linear. So if we do twice U plus V, so twice 0 plus negative 3, so negative 3, twice 2, so 4 plus 1, twice 7, so 14, 4 more, twice 5, 10, minus 8. So that's 2U's plus V. 1/3 of that would be negative 1, 5/3, 6, 2/3. So this would be W, which is a linear combination of U and V. Let's do another one. Let's suppose we have vector U1 to be 2, 3, 5, vector U2 to be 1, 2, 4, and vector U3 negative 2, 2, 3. And let's write V as a linear combination of those three vectors. So let's see how we can write V as something times U1, something times U2, something times U3. basically, we're going to have a system of equations. We're going to have a times the first one, 2, 3, 5. B times the second one, 1, 2, 4. C times the third one, negative 2, 2, 3. And that 1, 4. So if we think about this one as A, 2 times A, 3 times A, 5 times A, 1 times B, 2 times B, 4 times B, and the same thing with C, then 10 comes from combining the first elements on all of those. So 2A plus 1B minus 2C. 1 comes from the second elements, so 3A plus 2B plus 2C. And 4 comes from 5A plus 4B plus 3C. And we can solve that. However, you can think about this as augmented matrix where these are the coefficients. You can think of it as AX equal B, where we have 2, 1, negative 2, 3, 2, 2, 5, 4, 3, and we're trying to find A, B, and C such that when we put A, B, and C in, we get 10, 1, 4. So we can find the inverse here times that, and I'm just going to do that with MathCAD real quickly. Open up a new page. So I'm going to call A 3x3 matrix 2, 1, negative 2. 3, 2, 2. 5, 4, 3. And then our right side is 10, 1, 4. So 3 rows, 1 column. 10, 1, 4. Then if we do A inverse times B, we get 1, 2, negative 3. So A, B, C is 1, 2, negative 3. So that means we need one of these, 2 of these, minus 3 of these. Notice 2, 1 times 2 is 2, so 4 minus 3 times minus 2 is 6, so 10. 3, 2 times 2 is 4, so 4 plus 3 is 7. Minus 3 times 2 is negative 6. 7, negative 6 is 1. 5, 2 times 4 is 8, so 5 and 8 is 13. Minus 3 times 3 is minus 9, so 4. So we've expressed V as a linear combination of U1, U2, and U3.